Hello, everyone. Thank you for joining us today at WCNC 2022. My name is Xianyi Chen, and I will present our paper, a reinforcement learning-based access scheme for low latency and correlated traffic MTC networks. The presentation will be organized as follows. I will first give a brief introduction to our works, and then I will present the system model and the time frame structure, followed by our considered traffic model. Then we will get into the proposed access scheme. After that, I will show the illustrative results, and finally, we conclude the presentation. The machine type communication will become the main focus in the 5G and beyond wireless networks. The characteristics such as a massive number of devices and low latency requirements should be considered. In addition, devices can have correlated traffic due to possible related events. Devices near the occurring events will likely to be triggered to report the events, which may influence the packet's delay. So in this study, we considered MTC networks having a large number of devices with correlated traffic and different delay requirements. We aim to maximize the throughput while minimizing the delay violation without the knowledge of the device traffic parameters and the event location at the base station. Then for the system model, we considered MTC networks having one massive MIMO base station with M antennas and D single antenna devices. We divide the time frame into two segments as shown in the figure. A ground-based segment reserves time slots and preambles for the devices allocated to this segment. And we have another ground-free segment for the rest of the devices. Those devices have to content for transmissions by P persistence aloha with probability P. Devices having packets randomly choose a preamble and transmit the preamble followed by its data. If the preamble is selected by any other devices, the preamble collisions happens and the transmission is failed. Then to understand the correlated traffic model, let's look at an example figure here. So if we have an event happening right here, we can see that the nearby devices 1 and 2 are likely to be triggered into alarm mode, and the devices 3 and 4 are less likely because 3 and 4 are far away. In other words, the devices having spatially correlated traffic that can be modeled as a two-state Markov chain. Devices in the regular states have low arrival rates, and devices in the alarm states have higher arrival rates. And the probability of triggering into the alarm states, Px dt, is higher when the devices is closer to the events. And furthermore, each device has a low latency deadline LD max, and the devices peekbacks and extra bits QDT to their packets to tell the base station their queue status. Once an event happens and we receive packets from some devices, the spatial correlation means that the nearby devices have a higher chance of having packets, and the resources should be allocated to those devices to reduce the latency and improve the throughput. We formulate our problem as follows. At the beginning of any time frame, the base station schedule the devices in the ground base segment with an allocation matrix X and calculate the access probability of the devices in the ground free segment as a vector P. Correspondingly, the objective function is shown by the equation 1. The ST is the throughput with delay constraint at time t, which is equals to the total number of packets received at time t minus the number of received packets that violates the delay deadline at the time t. The C1, 1, 2, and 3 ensures that each devices can only transmit once in either ground base or ground free segment in each time frame. The C14 ensures the access probability is between 0 and 1. And finally, the C15 is to limit the length of the ground base segment. Since the base station don't know the traffic model parameters and the event location, it is infeasible to obtain the delay characteristics for devices. So it is hard to derive an expression for the objective function to optimize it directly. The algorithm needs to learn and exploit the traffic correlation. But in this case, the supervised learning is not suitable because it requires a simple collection process at the start of the system operation. And therefore, we can use reinforcement learning because it can train during the system operation so that we can remove the initial data collection process. So here we have a figure to illustrate how the RL agent works. And the RL problem are usually modeled as a Markov decision process. And the goal of the RL agent is to take action that maximize the cumulative reward. However, if we directly output the allocation decisions X and P from the RL agent, the output dimension might be too large to converge. Directly outputted X and P by the neural networks might be infeasible or invalid. Therefore, we reduce the action space by outputting a non-empty Q probability and use the algorithm 1 in reference 3 to calculate the X and P. This algorithm will iteratively increase the length of the ground-based segment and allocate the devices have high non-empty Q probabilities to this segment and calculate the access probability for the rest of the devices in the ground-free segment until the estimated throughput cannot be further increased or the length of the ground-based segment reaches its maximum value. And then for our RL agent, the environment will be our simulation process. The input state vector of each devices contains the time duration of the last successful packet transmission until now, the duration of the creation timestamps of that packet until now, the delay deadline, and also the piggyback bits. The action vector will be the theta dt as we mentioned before. And the reward will be the throughput with delay constraint as in the objective function. To maximize the return, we use the deep deterministic policy gradient algorithm. The Q function is the expected return given by action AT when the system is in the state ST and uses the policy pi. The DDPG algorithm use a deterministic policy so that the inner expectation is avoided as shown in the equation 4. Also, we can just output actions by using the piggyback bits to improve the convergence and ensure safe operations. For each device D, if the QDT equals to 1, we set the theta dt equals to 1, regardless of the value outputted by the RL agent. So here is our algorithm. We first initialize the actor and created networks and their copied target networks, and the replay buffer to store the transitions for training. Then in each time frame, we obtain the theta dt as the action from the actor network based on the current state and add a noise to explore different actions. Then we adjust theta dt based on the piggyback bits, and then we pass them to the algorithm 1 in the reference 3 to obtain the X and P. Then after the transmission, we will obtain the ST as the reward value and also the next state vector. We will store the transition samples to the replay buffer and randomly sample a batch from the replay buffer to update the created networks by minimizing the loss as shown in this line, and also update the actor networks by maximizing the function J as shown here by its gradient. And finally, we update the target network weights as shown in these two lines. So next, I will present some illustrative results Here are some simulation parameters and the actor-credit network structures. We will compare our algorithm with 3 different agents. The RLWA agent is using the DDPG algorithm, but without the action correction. The non-statistic agent knows all traffic model parameters and the event locations to calculate the theta dt. The random agent will randomly generate the theta dt from a continuous uniform distribution. If the piggyback bit is 0, and set the theta dt equals to 1 if the piggyback bit is 1. We use the normalized average throughput with delay constraint and accumulative delay ratio as the performance matrix. So let's look at the throughput. The S star of the RL agent is lower than the random agent at the beginning, as we can show from this part. And after the 200 time frames, the RL agent achieves a higher value since it has learned a good policy. The RLWA agent, whereas is the lowest, since it does not have the action correction, so it converts to a bad local minimum. Overall, the RL agent gives higher S star than the random and RLWA agents, while slightly lower than the non-statistic agents. And for the delay, the RLWA agent and the random agent have a higher delay ratio than the RL and non-statistic agents. We noticed that the RL agent has a higher delay ratio than the non-statistic agent at the start, as we can see from this part. However, it has the lowest delay ratio after around 750 time frames. This is because the non-statistic agents only maximize the total number of packets without the awareness of the delay. Therefore, the non-statistic agent receives more packets than the RL agent, but it's more often the delay constraint than the RL agent. And finally, we plot the value of the actor network function J over time for the RL and RLWA agent. The RLWA agent converges to a bad local minimum since it does not have the action correction. This action correction helps the RL agent to have the action with better rewards to learn from, so it converges to a better local minimum. So in a conclusion, we propose an RL-based algorithm with action adjustment to maximize the throughput and minimize the delay violations for the MTC networks with correlated traffic and delay constraints. And the simulation results shows that the great benefits of the action adjustment compared to the RLWA agent, and rivals that our proposed RL agent has a good throughput with delay constraint and a lower average delay ratio than the non-statistic agents. And here are some references for the presentations. And that's the end of the presentation. Thank you for listening.